lecture 5. A quick recap of what we have done in this course so far. So, we have learnt about Telegon's theorem, we have learnt how Telegon's theorem was used to prove reciprocity in networks with linear bilateral elements. Unfortunately, we found that while reciprocity is great and very useful in practice, we found that it is not applicable to a large class of networks that we often deal with, namely those with control sources. And then we said, oh well, there is a fix, and that is by using the concept of interreciprocity, where the idea is that while you cannot interchange the location of the excitation and the response in the original network, it is always possible to come up with another network which is called the interreciprocal network or the adjoint network, where you can interchange the role of the excitation port and the response port, right. And this is immensely useful in practice, simply because you have you are now in the position to be able to find multiple transfer functions to a single output, either voltage or current, in one shot, without having to rerun the computation again and again. And as I was mentioning yesterday, this is routinely done in all circuit simulators, whether they are doing noise analysis or whether you are doing transfer function analysis. Good. So, having seen that, now let us go move forward and look at or rather refresh our memories about ways of writing circuit equations. In your earlier classes, you have likely seen you have probably seen many ways of doing this. The nodal analysis is probably the first one that comes to mind. Then there is mesh analysis, etc., etc. For good reason, nodal analysis, the basic framework of nodal analysis is very popular, and the reason is that it often involves more work to find meshes and then find the and then once you found the mesh currents, then you do some more operations to get the branch currents. On the other hand, nodal analysis gives you in one shot gives you all the node voltages, and since the branch relationships are known, the branch currents can also be found in one shot. So, let us go through a quick refresher. So, let us start with networks which only consist of resistors or conductors and current sources. And again, I am going to take this ice cream cone network as an example. So, I am going to choose some reference, some node as the reference voltage or ground, and we will have the conductances are G1, G2, G3, G4, G5 and G6, all right. And the nodes are numbered 1, 2, 3, and perhaps we have some sources, say IS1, and we have another current source exciting the network, that is IS2, right. How do you write the nodal equations? Well, it is very straightforward, as you have seen in the past. The nodal equations are simply expressing Kirchhoff's current law at a node, right. And once you see that, it is not necessary to write equations one by one carefully staring at the network. We have already seen this in your basic electric circuits and networks class. What are the unknowns that we are trying to solve for? The node voltage vector, which is V1, V2 and V3, right. And if you write Kirchhoff's law at node 1, you can go through it the long form, or recognize that you can do it element by element, as you have seen in your earlier classes. right. So, I'll since it's a long time that you saw this, let me just write Kirchhoff's law at node 1 to give you a quick refresher on why we do what we do. So, if you write KCL at node 1, what do we see? It's G1 times V1 plus G2 times V1 minus V2, right, plus G6 times V1 minus V3 equals, that is the sum total of all the current going out of the node, and that must be equal to the current going into the node, and that must be equal to, in this case, minus IS1, right. Okay. And likewise KCL at node 2 gives us G2 times V2 minus V1 plus G3 times V2 plus G5 times V2 minus V3 equals, no, at node 2, what is the sum total of all the current flowing of the source exciting, oh sorry, that is IS2 indeed, thank you, all right. Okay. So, now you stare at this and then say, oh well, so G2, this particular conductance appears only in KCLs for node 1 and 2, correct, and therefore, and how does it appear in this matrix, in the conductance matrix? This is the conductance matrix. You can arrange these equations in matrix form, and the reason it is called the conductance matrix is because every coefficient corresponds to the conductance of some element or the other, and therefore, as far as G2 is concerned, for instance, where do you think, which rows will G2 appear in? Well, G2 goes between nodes 1 and 2, so it must appear in the first 2 rows, right, and G2 relates which two node voltages? V1 and V2, and therefore, it must also appear in the first 2 columns. So, between 1 and 2 basically, how does it appear in the first row? How does it appear? What? Okay, can you fill up the entries of the matrix? Can you tell me which all of those entries in the matrix will correspond to G2? To G2, yeah. So, these are the 3 rows. These are the 3 columns corresponding to V1, V2 and V3. So, can you help me write the nodal equations? What will happen to G2? It will appear in the first 2 rows and in the first 2 columns, and as you can see, it must be G2 minus G2 minus G2 and G2, right. And since G2 does not appear anywhere else, we can now forget about G2, we are done, right. What about G1? First row, first column. And what about G3? Second row, second column, very good. What about G5? Between 2 and 3, so that is G5 minus G5 minus G5 and G5. That is done. What about G6? Between 1 and 3, So, that is basically that is done. Then what about G4? Well, that only appears in the third row, third column, correct. And this must be equal to, where does IS1 appear? It must appear between nodes 1 and 3. So, in which of these on the right hand side, which of those rows will it appear in? So, it is minus IS1, because that is the current flowing into node 1, and this will be plus IS1, and likewise IS2 correct. So, once we have done this, there is no need to go over the same procedure of writing the KCL at every node and then arrange them as a matrix. You can simply look at the network and write the equations. And what is the within quotes algorithm? If you see a conductance between two nodes A and B, and let us call this G, right. What comment can you make about the G matrix? So, we have the G matrix, the conductance matrix, all right. It has the Ath row, the Bth row, it has got the Ath column and the Bth column. And how does this appear? How does this appear? It appears as G minus G minus G and correct. And likewise okay, and likewise if you have a conductance only going between a node and ground, it only appears on the diagonal, right. And this is what is called the stamp of the conductance right. All that this is saying is that, well, by looking at the number of nodes in the network, you already know the size of the conductance matrix. So, you can initiate or initialize a conductance matrix, a matrix with that size, and then you go element by element and replace. I mean, when you go to a particular element in that list of elements you have in your network, you simply plop in that appropriate stamp of that element into the matrix, and then you are done with that element. You do not have to worry about it anymore, and then you have a list of elements. So, you keep going through the list, and then when you end the list, you are done, correct. Okay. So, that basically this, I mean, if you can describe it so clearly, it basically means that a computer can do it. There is nothing deeply philosophical or this thing about it. It is just a very straightforward algorithm, right. So, on the left side you have the conductance matrix. These are the node voltages which are the unknowns. On the right side you have the source matrix or source vector, I must say, where you have all the independent sources, correct. Okay. And once you basically find, so let us call this node voltage, this conductance matrix, let us call that G, and then the node voltage vector, let us call that V, and this is let us call that I sub S for the source voltages. Okay. So, the nodal equations can be written as mGV equals right, and it is straightforward to find V as simply G inverse times. Is that clear, people? I mean, this you must have seen, so there is nothing new about this. I mean, you must have seen this before multiple times. It is just a refresher. All right. So, so we have covered, therefore, in principle, we have covered networks with conductances and current sources. Unfortunately, these are not the only elements that we encounter in practice. Let us see what happens, for instance, if we have, I am going to just simply avoid clutter, I am going to remove one of these things and then replace it by a voltage source. All right. And we like to wonder, how, I mean, of course, we know that if you write the equations, you can come up with some set of equations which eventually works, right, and you will be able to solve the set of equations. But the question is, can we come up with a clean way of describing, how you go about writing the equation, so that it can be done on a computer in a systematic fashion without having to have intervention every time, right. So, the problem with a voltage source is that the current through it is unknown, correct. So, well, then we say, oh well, let me put this in red actually. Then I say, oh well, we do not know the current through the voltage source, so it is an unknown, and we assign an unknown current IS1 through the voltage source. And this is a voltage, and this unknown has to be determined just like any other unknown. Okay. So, earlier we had the G matrix, correct, with conductances. I am going to not copy and paste the same thing all over again. So, I am going to call that the G matrix, right, which is the same as we saw earlier, and again this is node 1, this is node 2, and this is node 3, and this is node 1, node 2, and node 3. We now have, apart from, what are the unknowns now? What are all the unknowns? V1, V2, V3 are the unknowns. We also have an additional unknown, that is IS1, right. So, let me just use a small IS1 here simply because it is an unknown, IS1, right. And so, if you write KCL for node 1, apart from all the conductances which we have already dealt with and gotten this matrix G, we now also have, if you write KCL at node 1, what do you get? What is the extra term you get? Remember, now there is an extra, I mean, apart from the currents flowing through these guys, which have already been accounted for in this G matrix, there is also an additional current which is flowing out, which is minus IS1. So, where do you, so what do you think the equation will be in the first row? What should I do? What should I do? Where will we put the minus 1? Yes? First row? Last column, very good. So, you put a minus 1, right. And likewise, where else do you think you will get a, so the voltage Vs1 is connected between nodes 1 and 3. So, where do you think, what do you think will happen to, how will I account for IS1 flowing out of node 3? Very good. So, basically you can see we have a minus 1 there, we have a plus 1 there, and what comment can I make about the element there? that is 0 because IS does not touch node 2, correct. So, we have one more unknown. So, we better have one more equation, and what is that equation? Well, the extra equation is that V3 minus V1 equals Vs1. So, what should I do? This is the how should I write that in this matrix? Fourth row minus 1 0 1 0 must be equal to what should the right hand side look like? The right hand side, remember, must have only the independent sources. So, where are the what are the independent sources? The first 3 rows will have only the independent current sources. So, what are the independent current sources flowing into node 1 is 0, IS2 0, and what should be there? Vs2. Sorry, Vs1, sorry. Is that clear? All right. And so, again this is the original conductance matrix augmented with something else to account for the voltage source. And please note, I would like to draw your attention to the following. This is always going to be, what comment can you make about this part and this part? If you take that part, this is going to be simply the transpose of that, right, and I think it is pretty apparent how that happens. Okay. So, the current flows between the current in the voltage source flows between the 2 nodes, and the voltage source forces the difference between those 2 nodes to be something. So, it stands to reason that this row is simply the transpose of this column. Is that clear? Now, okay. Now, if you had another source, what do you think you will do? Let me just make life a little more complicated by say, for instance, Vs3 for instance. Okay, what do I do now? I mean, do I need to start all over again, or can I just simply kind of well, straightforward, as you all point out, very good. So, this current is I am going to call that IS3, right, and what do I do? Well, I add another, there is an extra unknown, the extra unknown, and that is what is that saying? That is between nodes 2 and 3, and how do they so what should I do? The new unknowns are basically V1, V2, V3, IS1 and IS3 are the unknowns. Yes, so what should I do, please? So, for every extra voltage source, you augment this original conductance matrix by one extra row and one extra column, right? And what happens to this the new row and new column that we need to add now? What is that? So, Vs3 goes between nodes 2 and 3. So, it should basically it must be 1 and minus 1, correct? Is that clear, people? And likewise, what should this new row be? 0, 1, minus 1 and this is 0, all right. And as usual on the right hand side, well, the first 3 rows are basically, well, 0, IS2, 0 like we had before, and you have the independent sources Vs1 and Vs, correct. So, therefore, we are now in a position to cleanly write. So, this is basically the augmented conductance matrix. All right. What comment can we make about G? Can we make any comment about the structure of G? Well, it is symmetric, because if you remove all the current sources and you remove all the current sources and physically remove all the voltage sources, then all that you have is conductances, which are obviously, if a conductance is going between 2 nodes, it appears symmetrically across. Okay. All right. And you can therefore solve this set of equations and then in one shot get all the voltages and node voltages and currents through the independent sources. So, this is telling us what to do. This analysis basically telling us what to do when you have a voltage source. So, when you have a voltage source between nodes A and B and Vs, you add a new unknown Is, right? And what happens? You had the original G matrix, correct? And then what do? You augment it with so you have the 8th row, bth row, 8th column, bth column. So, what should you do? What did we do when, and remember, you should be familiar with this stuff so that you will be able to look at a network and write down the equations without the matrix without having to go through the whole. Very good. So, basically you must have 1 here and minus 1 here. Okay. In the 8th row you put a 1 and the bth row you put a minus 1, and likewise, so that the stamp of a voltage source if we had nodes A and B is the following, and that is you had the 8th row and the bth row as well as the 8th row and the bth column, and you add an extra. So, this is Vs, this is the current extra variable Is, and with the augmented conductance matrix, what you do is you put in a 1 and a -1, right, between the nodes A and B, in the 8th and bth rows, that corresponds to the accounting for the current that is flowing through the voltage source, and you put in 1 and -1 for in the 8th and bth columns in the last row, and this matrix is going to, that entry is going to be 0. So, this is the node voltage vector, this is the original conductance matrix of the network stripped of all current sources, independent current sources and voltage sources, and then you have this new variable Is, and this is equal to what do you have? What should you have here? Here you have all the independent current sources, and then now you have Vs, right. So, the way this method of accounting for voltage sources, or in other words accounting for branches where the branch current cannot be expressed as a linear function of the branch voltage, right, is basically, this is an extension of the nodal analysis that we know already, and this is what is called the modified nodal analysis. And as we have seen so far, if we have networks with conductances, current sources and voltage sources, I mean this the algorithm for writing these matrices is very clear, right. You just make you describe the netlist, right, and in a computer you have a parser which takes a circuit diagram that you draw and generates a SPICE netlist, and you keep going line by line in that netlist, and you look at the element and you can simply plop its respective MNA stamp is what it is called, right, into the matrix. So, if you have n nodes, right, in the network, or let us say deliberately choose n plus 1 nodes in the network, okay, and m current sources and p voltage sources, what comment can you make about the size of the augmented G matrix? Well, you have n plus 1 nodes in the network, one node is ground, you have n other nodes whose voltages you need to find. So, you will have n unknowns as far as the node voltages are concerned. You have p voltage sources. So, out of p voltage sources, the currents through the p voltage sources are all unknowns. So, the total number of unknowns is n plus p. So, the augmented G matrix is what is the size of the matrix? N plus p cross n plus p. The unknown form a what vector? How many unknowns do we have? N plus p. So, this must be an n plus p cross 1 vector, and the source vector obviously better be also n plus p cross 1, correct. And where is the source vector? The lower 3, I mean the lower p entries will correspond to the strengths of the voltage sources.